Now, the stiffness matrix that we have derived, which is Ke, is just related to a standard triangular element that we drew out here on the page, right here. Now we see that the triangular element itself is lying in its own local coordinate frame as usual, because we have to consider that this element is actually part of a much larger structure, right? So it's lying somewhere arbitrarily in space. Now, with respect to the global coordinate system x, y, it's actually it's aligned differently. It's aligned in a different coordinate axis. That means we need to also have a transformation from the local to the global in this case. And of course, there is a certain way of doing it. So I will just give you a small introduction, basic concept about how it has to be done. And if you would require it, you know that you have to find out or you have to align the element in a certain way to the global coordinate axis. And of course, if you have a bigger structure, that means you have to do this transformation for every single element based on the element itself placed with relative to the global coordinate axis. So let's come here now finally to the transformation part. If we are going to look at transformations, then it's good first to describe a certain element which is lying in space. So we're going to consider a similar element that we saw before. I'll make it this time slightly bigger because it's easy to see. Then I have the global coordinate axis, which may or may not be completely straight, but you get the idea that it has to be perpendicular. And then you have x global, y global, and then you have the three nodes I, j, and k, and at each of these points you have all the degrees of freedom that you require. Yeah, so you'll have local degrees of freedom and you will have global degrees of freedom, which have been then finally transformed. Okay, so if you look at this element particularly, then we see that it is aligned in a certain way, right? So we also have to define what is this local way of defining this certain element's direction. So the conventional way to do it is that you take this point I as your origin. So let's write this as O. Then you have in the direction of ij, you define your axis OY, and perpendicular to OY is OX. I'm going to write this as small letters so we know this is local and the other one is global. So now I have OX and OY. Okay, and OX, OY are also perpendicular to each other, so they're lying in the XY plane, which is local to the element. So that's a way we have to describe the angle from the local to the global. And of course, you will see that all the different edges of this triangle are lying at a certain angle with respect to this OX and OY. So we'll have to describe the transformation matrix taking all those points into account. So in order to generate the transformation matrix, let's call the transformation matrix T. In order to generate this transformation matrix, we need to have the direction cosines of these lines, the OX and the OY, with respect to the global axis X and Y. Now, since the direction cosines of the line OY is same as IJ, it's quite easy to write the direction cosines for that. So the direction cosines, as you might remember from your previous study somewhere, is always written with letter L. Yeah, so I can write the direction cosines of OY because it coincides with IJ. We can write Lij to be equal to xj minus xi by the distance ij, which would be the length of ij. Mij would be equal to yj minus yi by dij. Now we are looking at the system in 2 dimensions, so this is enough. But if you had a third dimension, in this case you don't, then you would have a nij to be equal to zj minus zi by dij. This would of course only count for the third dimension. Okay, so we have the Lij and the Mij, which are the direction cosines for OY or IJ, which are coincident. And at the same time, we know that the distance dij between these 2 points can be given in 2D space as xj minus xi square plus yj minus yi square, of course under a root. And if you have a third dimension, then you would write zj minus zi square. Close it, and then you have to the power half or square root. Okay, and these of course xi, yi, xj, yj are the coordinates of these particular nodes. So maybe I can also write them here just to be clear. So you have xj, yj and xi, yi, and this would be then xk, yk. We've seen this before, but just as a reminder, it's good to put it on the diagram for clarity. Now, since the direction cosines of OX are very difficult to compute because we don't know where the point is, right? We have to find a point on the line OX for that case. So what we do is that we can easily draw a perpendicular. We go back to a different color. We can draw perpendicular from K to the line OY. Yeah, this would be a perpendicular, and we would get a certain imaginary point on this axis, which we can write as point P. So we can get PK as your perpendicular, and we can define the direction cosines for PK. And there is a whole process that goes on behind finding out where P lies and how you can define XP, YP in terms of the coordinate system and using the direction cosines of IJ, etc. But I'm going to skip all of that in this video. I will put in a little a page from a certain book. I'll ask you to follow a certain reference book, which gives you a much better idea of how it has to be done in more details, because it's actually not quite relevant to us. We are not going to use it beyond this point, but it's good to know how the focus of the transformation matrix is, why we need it, and how we can find the transformation matrix in general. So in the same way, if we have PK, which is parallel to OX, then we can write the direction cosines of PK. Yeah, if we want to say OX, we can write it as PK. So in the same way, we have LPK, which will be written as XP minus or xk, because k comes afterwards, xk minus xp by dpk, and mpk is equal to yk minus yp by dpk. Yeah, and you just have to find out all these relations. Now we also have to know that the direction cosines, of course, have to be perpendicular to each other, right? That means if if I have these relations now, so I have Lij, Mij and Lpk, Mpk as the direction cosines, then when I want to put them back together and find all the relations, then I have to make certain assumptions that they are perpendicular to each other, etc. And we will be able to solve for the dpk as well, so that we can put this back in the equation here and get the real direction cosines. So once we know these particular cosines, Lij, Mij, Lpk, Mpk, then we can write the transformation matrix to be constructed out of these direction cosines. Okay, and how exactly do we do that? The transformation matrix T for a system such as a triangular membrane element has 3 particular nodes, right? That means we have to have a certain matrix which is catering to the 3 nodes. If the stiffness matrix is dependent on the number of degrees of freedom, and in this case the number of degrees of freedom are 6, because you have uijk and vijk, then the stiffness matrix is given as a 6 by 6 matrix. If the stiffness matrix is a 6 by 6 stiffness matrix, then square matrix, and the transformation matrix also has to be a 6 by 6. Now we know from our previous discussions and also derivations, we have just calculated the direction cosines sorry, I should write the other one first, LPK and MPK, which coincide with direction OX, and Lij and Mij for the direction OY. Yeah. Now this can be used for transformation in general of only a certain node. Yeah, for any node which is present, for example, if I just consider the node I, so I have the node I, then I have a certain local displacement ui uj. Let me write it as ui uj. And say suppose the global is in a awkward direction like this, so I have capital ui and capital uj, then I know that according to the direction cosines of ox and oy, so if this is o and x and y, then I will be able to find out what is the transformation, yeah, with respect to these direction cosines. So that transformation can help from to go from lowercase ui uj to uppercase ui uj, or local to global. So we can name this particular transformation matrix as T local. Okay, so T local is given as this. Now we can apply this transformation to every node, because you have the same transformation we will use for the same for one element. That means we can write then the final total global as in for the entire system. I don't want to use the word global here, so I will use element. So the element transformation then can be written as T local, or actually it would be a better idea to write this as nodal. Sorry about this, but just thinking along. So if I have T nodal, and I know that I have 3 nodes in the system, then I have T nodal for the first node, T nodal for the second, and T nodal for the third node. And at the same time, I have other nodes which are not participating at that time. So when I'm talking about node I, then I'm looking at the first row. So there will be a vector, 0 vector. So if I write this as vectors or matrices or something, let me write this as matrices. And another 0 matrix for all the locations that do not have any contribution at that particular transformation point. Can be written as this. So what I need to do is I just need to substitute the T nodal here, yeah, in all these locations. And if I substitute that, then of course here T nodal is given to you, and the matrix 0, the 0 matrix here is also 2 by 2, because T nodal is 2 by 2, is given as a matrix that looks like this. So if I put everything together, then this 3 by 3 matrix, which or sort of like a tensor which contains of more matrices, then it would look like, it would become a full-blown 6 by 6 transformation matrix. So if I want to make it explicit and I want to write it down, then I can write the T element can be written as LPK MPK LIJ MIJ 0 0, twice the same matrix. Then again once LPK MPK LIJ MIJ, and again this same, because the first 2 nodes are not participating. In the last one you have LPK MPK LIJ MIJ, and this becomes your full-blown element transformation matrix, which is 6 by 6. And of course this has to be then multiplied with your local displacement, for example. Then I would get UI, VI, UJ, VJ, UK, VK. So this is now my final transformation matrix from going from local to global. Yeah, and sort of makes sense. So I have 6 by 6 and this is 6 by 1. So that works out fine. And finally, the global stiffness matrix can be given as T transpose K of the element times T. So K element is the local stiffness matrix, and this is the stiffness matrix that we have been finally looking for.